Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to discuss on the effects of concentration in a galvanic cell, and this is going to be the concept of the Nernst equation. So for that case, we are going to see on how we can be able to represent the effect of this concentration in a cell, and also we're going to use a sample question at the board to try and find out how we can be able to apply this concept of Nernst's equation. So without further ado, thank you and welcome. So as I've said, today we're going to look at the concept of the Nernst equation. And this basically deals with the effect of concentration of each of the reactions in electrochemical, on the electrochemical cells. And basically we're going to look at the concept in a galvanic cell that pertains to Gibbs free energy. Now we have talked that the free energy related to the cell voltage can be given by an equation, and we had represented Gibbs free energy in form of delta G. Now in this case we said that for the free energy related to the cell voltage, we can be able to give this equation in form of negative NFE, where N represents of course the number of electrons which are involved in the reaction from the mole ratio of that half equation. F represents the Faraday, which is the charge, and E of course represents the energy, that is maximum electromotive force. Now of course we're going to see how this particular equation is going to change into another representation that we're referring to, the Nernst's equation. But we can remind of ourselves of a few concepts that we have already learned from our previous discussions. We talked of the concept of a cell as a device that converts chemical energy to electrical energy in form of chemical reactions which are taking place, and then there's a potential difference which is realized in the process. And therefore this gives us the concept of an electrochemical cell. An electrochemical cell, of course, which is another definition for this device that is consisting of course, chemicals that are producing electricity. And we said that this entails a spontaneous redox reaction that leads to the production of this electricity. Therefore, this particular electrochemical cell can be regarded using or referred to using another term that is known as a voltaic cell or a galvanic cell. So whenever we are trying to mention about the concept of a voltaic cell or a galvanic cell, it involves a spontaneous reaction that is producing a redox spontaneous reaction that is producing electrical energy. And of course, apart from this, of course, as we have talked about the concept of electrochemical cell, and this involves spontaneous redox, of course, reactions which are producing electricity. Now, under electrochemical cells, the voltaic or galvanic cell is one of the examples of the electrochemical cell. There's a second one that we refer to as electrolytic cell. Electrolytic cell. So therefore, the type of electrochemical, this concept of electrochemistry has got two specific concepts, whereby we have a voltaic cell or a galvanic cell, and then there's a second one that is known as electrolytic cell. Now, when we were trying to talk about the concept of electrolysis and of course the the electrolysis, we say that there is electricity or an external source of power that is used to initiate the process of electrolysis. External source of power, which can consist of maybe a battery, etc. So this basically deals with the concept of electrolytic cells. Now for this one, it is spontaneous reactions which are producing a potential difference. So therefore it does not involve the concept of external sources. So that basically is the difference between the galvanic cell and the electrolytic cell under this broader topic of electrochemical cells. So basically electrochemical cells contains of a galvanic cell, the electrolytic cell, and the difference is that this one, the potential difference is realized due to spontaneous reactions. The second one, the power is derived from an external source, which can consist of a source like a battery. Now in this case, we talked about the concept of Gibbs free energy, which was being represented as such. But this was a result of work, and we had defined Gibbs free energy as the negative maximum work that can be done by the system. So in this case, we're going to see the relationship still holds for Gibbs free energy, whereby we can define it as a free energy or Gibbs free energy which referred to the energy available in the system to do work, and is different from the total internal or the total energy change of a chemical reaction. So basically we're just going to refrain ourselves or just restrict ourselves to this particular concept. And of course from this we said that this one can be, work can be defined as QE, and of course we had said that Q can be related to NF, and in this case of course this one leads us to this broader concept of a definition of Gibbs free energy. So in the Nernst equation we're going to use this relationship whereby Gibbs free energy is going to be represented as the standard Gibbs energy plus RT, the natural log of Q. So these are different as another way to represent the Gibbs free energy. And we're going to encounter this equation somewhere, but we proceed with this using the relationship between Gibbs free energy and this representation using the number of moles, the charge, and the maximum work. So therefore this equation can be rewritten in the form of a negative MFE from this relationship is equals negative NFE standard plus RT natural log of Q. Q now in this case represents the reaction quotient, and then R. Okay, I can just list these specific terms later. Let's just find a simplified form of this specific equation first. So in this case, this relationship, the connection between those two equations is going to give us this relationship, whereby we're going to find that E is equals E standard minus RT natural log of Q over NF. So basically we have done a division for negative NF to all parts of the equation, and we have already attained that one as our final equation. Now this final form of this equation is what we refer to as the Nernst equation. And of course, it's going to give us the the relationship, of course, of the concentration that we talked about of electrochemical reactions in galvanic cells. Now, at some conditions of room temperature, I'm just going to list some of the conditions that we have already discussed here. At room temperature, the value for R is going to be 8.31, for this is a constant, and then the value for T, because this is temperature in kelvins, is going to be 298 kelvins. F, we said, is a Faraday 96485 coulombs per mole, and then the natural log of Q is going to be 2.303 log of Q. So therefore, considering this condition that we have given at room temperature, for that, the Nernst equation is going to reduce to a form that is going to appear like this. So it is going to be E equals, so this equation is going to reduce into a form that is E equals E standard minus 0.0592 over N log of Q. So this basically is the equation that we refer to as Nernst's equation. This one and this one, but this one is under the room temperature conditions that we have stated there. So we are going to make use of this particular equation, the Nernst's equation, in order to find the solution to the problem that we have on the right side of our board. So I just do away with this. So therefore, our question states that what is the potential of a half cell consisting of zinc electrode in 0.01 molar zinc sulfate solution at 25 degrees centigrade? E standard is equals 0.763 volts. So the approach for us in trying to find a solution to our problem with this other side, I can just try to change this to this other side, which is E standard minus 0.0592 over L log of Q. So you are aware with this. So we're going to use that Nernst form of the equation, and this one is going to give us for zinc in a 0.1 zinc sulfate solution, we're going to experience oxidation reaction of zinc being oxidized to zinc ions plus 2 electrons. And from that other equation, for the oxidation of a half cell, we're going to have that equation represented as A is equals E standard minus 0.0592 divided by N. So in this case, for us, our N is going to be equals to, but we can just write our N, the log of concentration of the zinc and for this oxidation reaction. So therefore, doing a substitution for that one, we are going to have our N as 2 from this number of electrons, or the ratio of the mole ratio of electrons, and our E standard from the question is given as 0.763 volts. So therefore, we are going to do this one substitution in this particular case and find that E is equals E standard 0.763 minus 0.0592 divided by number of electrons is 2, and then this is going to be 0.01 molar that we are given there. So therefore, this is going to reduce to 0.763 minus 0.0592 over 2 into negative 2. So basically this is going to give us, because of space, it's going to give us 822 volts as the potential of the half cell that is consisting of zinc electrode in a 0.101 molar zinc sulfate solution at that specific temperature. So basically this is how we're going to apply the Nernst equation in trying to find the potential of a half cell, given the other information that we have talked about, maybe at the room temperature, etc. So as we move ahead, we're going to encounter different ways in which we can be able to make a use of this Nernst equation in trying to find out solutions for the electrochemical processes that may be given in form of a question or maybe in our discussions. So that is it for today, guys. Bye. God bless.